Well, as you can see from behind me here, we're about ready to talk about what I consider probably the best part of this class. And I get excited when I talk about this because it is the bell curve. And the bell curve refers to normal distribution, and it's when we start getting into continuous probability distributions, where we're looking at continuous data, not discrete, and with the mean and the standard deviation, we can come up with a lot of really good stuff and a lot of good probabilities out there. And so this guy becomes the crux of everything that we're going to do, and that's why, as you can see here, I've labeled him as our friend. So what is the bell curve? It is our friend because if we understand the bell curve, we will understand normal distribution, and normal distribution from here on out through this class is extremely important. So there's a lot of different types of distribution. We can look at exponential, uniform, even U-shaped distributions, but we're going to stick with normal distribution because it is the most common by far. Where would you have something like exponential, as you see over here? Well, that's usually like waiting lines or something like that. And if you think about it, if you go to McDonald's and you go and order some food, it probably doesn't take more than 2 minutes, and you're in and you're out of there. So you would be from, let's say, here over. Oops. Need my pen in this case. There we go. Got our pen. And so let's say that's 2 at this point. But there is a probability, and there's of it happening, let's say, up to 4 minutes because of you got there right at 12 o'clock or something like that. But let's say you pull up with an entire soccer team and you want to order from McDonald's and it takes 20 minutes. Well, that's not typical. So in that case, you can see the exponential distribution is normally the way that that follows. And all these lines, what they represent is the frequency of something occurring, and then all the possible values being underneath here. So this, in this case, is our normal distribution. That's the exact middle point, and there's about 50% on one side and 50% on the other, and it is perfectly symmetrical all the way across. So looking at these different types of distributions helps us to come up with some different probabilities. And again, we're talking about continuous random variables, which means a value is not a discrete number. It's going to be a range if we're looking for something. So if we're looking at, let's say, the height of individuals, the probability of being exactly 5'8" is almost 0. But the probability of being between 5'8" and 5'9", there's probably a higher probability of that. And by the way, when I say the probability of being 5'8" is 0, that's 68 inches. That's not very likely to occur. But if I say 68 to 69, now I can look at that, and there's a lot of people that are between that, and I can come up with a range, a probability based on a range as opposed to an individual value. So everything we do in here is going to be based on a range. What's the probability of being between 68 and 69? What's the probability of being greater than 68? What's the probability of being less than 68? Never exactly 68 in terms of continuous data. Again, there's different types. You can see the different ranges that are shown on here, and we can easily come up with some different ones there. But we are going to, again, concentrate specifically on normal distribution. And normal distribution usually is where you've collected data, and it's part of a survey, and you have the data that ranges pretty much high and low, depending on whatever the middle point is for that data, and you can come up with different things for that. Let's use an example for this class, and then we'll use that to kind of go through some different things about this. But going to the whiteboard here, let's say that you have an average on a test of 80%, or just say 80, with a standard deviation of 7. So that's what you have, and this could be for the midterm for all students here on campus, being that way it's a population, and it's for the midterm for BIA 2610. With normal distribution, what this shows you is the middle point of your data is right here, and that's your 80. Now in this case, what is the most likely value to occur? Well, it's going to be close to the midpoint. So in this case, 80 is probably the most frequently scored value. And then from there to the right are values that are larger than 80. And to the left are values that are less than 80. And so what's the probability of getting an 85? Well, that might be something right here. And it is less frequent than the 80. And so then we can look at this and say, well, what's the probability of getting between an 80 and an 85? And we can make some different decisions. By the way, have you ever heard of a faculty member say that I grade on a curve? For grading on the bell curve. So that is a little bit of where things go. Now, think about this. We would love to say that there are a ton of students that get 100% on midterms, but the truth is not very likely to occur. So what's the probability of getting 100 or better? Almost nothing, and that's why you see this being so low. What's the probability of getting, how about a 30 on the test? Not very likely, again, pretty far away. So you can see that if it's greater than the mean, it's to the right. If it's less than the mean, it's to the left. Okay? Now, the way that we actually measure how far we are from the mean is with standard deviations. So here's where we finally get to use standard deviations. And what we get to do is determine how far we are based on the number of standard deviations. And you'll see why that becomes important here. But let's get through some more of the basics. First of all, again, you care about the mean and the standard deviation. The standard deviation will, again, tell us how far from the mean that we are. The highest point will be the mean. And if your data is perfectly symmetrical, which almost never happens, then the median and the mode should also be 80 if it was perfectly symmetrical. Your data can then move from one side to the other. And so if the average is then, let's say, a 75, go back into the whiteboard here, 75 here, that's now the average. Now you've moved your bell curve to the side like that. We can also look at it in terms of your standard deviation and say that that could be my bell curve in this case, but then what if my standard deviation instead is a 3, then maybe it looks more like that, and please excuse my non-symmetric bell curves here, because it's going to be closer to the mean because of less variability. So the larger your standard deviation, the flatter the curve will be, which is what you would see when it was actually at 7. Now, in terms of probability, we all know that it's between 0 and 100%. And if it's perfectly symmetrical, that means that exactly half will be on the right and exactly half will be on the left. So if 100 individuals took a test, we would expect the probability of being greater than the mean being 50% and the probability of being less than that 50% as well. Now, let's talk about those standard deviations. And if you go plus or minus 1 standard deviation from the mean, it includes 68.26% of all values. If you go plus or minus 2 standard deviations, it's 95.44. And if you go 3 standard deviations, it's 99.72. Let me show you what we're referring to on the whiteboard here. Let's go back and draw this. This being our middle point, if I go plus or minus plus or minus 1 standard deviation. In this case, actually, we'll go draw it correctly. We're talking about 87 on the one side and 73 on the other. So 7 less on this side, 7 more on that side. And what that tells us then is that 68.26% fall in that value there. You then go down to 66, and that's an 87 to 94. And that would be 95.44% of our values. And so in this case, the probability of being between a 66 and a 94 is 95.44%, which means 5% would be outside of that. And you go out a third standard deviation, could be a value that's actually not even likely to occur, which is 101, depending if there's extra credit, and 59. And that tells you that almost all, or 99.72%, fall within that range, which tells us basically almost everybody should fall in there. Is there a chance of being outside there? Of course there is, based on this distribution. But that's what we are talking about. It's called the empirical rule, and that's where the power of this really comes from. And we look at a lot of things where this is what we care about the most. And if we're in this range, we're considered kind of the norm. And if you're outside that, there's definitely a reason why you're outside of those regions. So did you do a 94 or better? It's probably because you did something different than the person that got the 80. What about if you were at a 59? You probably did something different than the person that got an 80. For example, like didn't do anything. So that's just a little bit of how standard deviations work with this. And if you can kind of see, as an example, look at 80 on here and 87 again. That's 1 standard deviation from the mean. What if I want to know the probability of that area there? Or the probability of being an 87 or better? Or the probability of being an 87 or less? Can I calculate that kind of stuff? And the answer is yes, using z-scores, as you'll see as we get coming up in the slides here. So again, here's what it looks like in terms of the empirical rule, plus or minus 1 standard deviation. Real important to understand this concept. And then looking at it in terms of normal probability distribution, we want to take the exact same thing and understand it in terms of a z-score. Now, keep it nice and simple. How many standard deviations am I from the mean at 87? I am 1 standard deviation. Keep drawing S's instead of the population standard deviation. That would be a z-score of 1. If I was to go out 2 standard deviations, that's a z-score of 2. If I would go out down here to, what was that, 66, that's 2 standard deviations. That's a -2 for a z-score. So z-scores are nothing more than the number of standard deviations you are from the mean. And an easy way to calculate that is, put it up here, z equals whatever value you're looking for minus your mean divided by your standard deviation. So if we do 94 minus 80 divided by 7 gives me a standard deviation of 2. And then if I know that value, I can come up with a probability out to that point. And in this case, it would be, well, you know, remember it was 95.4, half of that, and it would be 0.4772. And hopefully we'll see that as we get going through these slides here when we look at a table. And if I come out to this point, so that's 0.4772. This would be 0.4772 because this is a standard deviation 2 from the mean on this side, 2 from the mean on that side, which is then 95.44%, because I added those two up. So z-scores are nothing more than a point or number of standard deviations away from the mean. Let me show it to you one last way. And let's look at it in terms of how it ties together. So, two different standard deviations. Using the same data. What would then be the z-scores? Well, the z-score at the mean will always be 0. Again, if you do that calculation, it should work out to that way. At 1, at -1 standard deviations from the mean, and so on out. So that's kind of how it goes. It goes out to negative infinity on the left side, positive infinity on the right side. So again, coming up with that z-score is nothing more than x minus mu divided by standard deviation, and it always gives you the number of standard deviations from the mean. If you want to do this in Excel, it's just as easy. All you have to do is go in there and put in norm SDIS, S standing for standard, which is your bell curve, and you can see your different probabilities. For example, the probability of being a z-score being less than 1 is 0.8413. The probability of being between 0 and 1 is 3413. Now, remember, here you have a z-score of 1, and before we said it was 68.26%. Well, what's half of 68.26%? So when I add those two together, that's how I get that. So from 0 to 1 for a z-score, it's 34.13. From 0 to -1, which is basically the same thing, it'll give you that value up there, which you can actually see right here as well. That's actually this times 2. So using that is just as easy. You can also come up with the number of tails using the inverse. If you give a given probability, it'll come up with the actual z-score that corresponds to it. So if you put in a probability of 0.975, you'll get a 1.96 z-score, which just means that would be out here at 1.96. And at this point, let's look at an example. And I'll tell you what, let's break this up into a separate video to make it easier. But let's look at this just to start with. So we've got a replenishment order for oil based on 20 gallons, and we want to know the probability of running out. And so we have to look at this as how often we would run out if we were to replenish at 20. So let's look at this example for the next video here, and hopefully this will help you in understanding z-scores.